Hey everybody, here's another set of problems, this time involving L'Hopital's rule. And let me just remind you what L'Hopital's rule is. If I take some sort of limit of a ratio of two functions as x approaches some value, right, could be 0, infinity, or something else, and if I look at the top alone and this approaches 0 or infinity, and at the same time g of x approaches the same thing, so either 0 or infinity. Okay, it could be plus or minus infinity, but that doesn't change anything. The point is that they both approach either 0 or they both approach some type of infinity. Then, to compute this limit, this is equal to the limit of, I just take the derivative of the top divided by the derivative of the bottom. So let me start with a really simple example here, right? So problem 1, and I'll show you how to use this. Basically, I'm looking at the limit as x approaches infinity of e to the x over x squared. So notice, as x goes to infinity, e to the x goes to infinity, right? Its graph looks like that. And x squared also goes to infinity as x goes to infinity. So we are in the infinity over infinity case of L'Hopital. So let's go ahead and apply the theorem. This is the same as the limit of derivative of the top is e to the x, derivative of the bottom is 2x, and of course this is as x goes to infinity. So now I look at this again, and I notice that the top approaches infinity, and so does the bottom. So I have to then apply this one more time. So again, by the infinity over infinity case, this is the same as the limit as x goes to infinity of, okay, the derivative on top is just e to the x, nothing changes there. The derivative of the bottom is now 2, and as x goes to infinity, the top goes to infinity, the 2 is a constant, so this whole limit is infinity. Okay, problem 2 now. What if I were to compare limit as x goes to infinity of x to the 12th power divided by, so I'm comparing x to the 12th by e to the x plus x squared, right? In other words, I want to see which one of these is a larger type of infinity. Well, the top goes to infinity, the bottom also goes to infinity, right? Because both of these go to plus infinity, so I'm adding those together. And that means I have to use L'Hopital's rule. So this whole thing is now equal to the limit, take the derivative on top, so that's 12x to the 11th, over, take the derivative on the bottom, that's e to the x plus 2x. And the same thing happens again, right? Both the numerator and denominator don't go to infinity, so I apply L'Hopital's one more time. So this is the same as the limit. On top, I have 12 times 11, which is 132 x to the 10th, divided by e to the x plus 2. And this same thing happens again. So what keeps happening is I keep getting infinity over infinity, but every time I apply L'Hopital's rule, I drop the power of x by 1, which means eventually, if I repeat these enough times, what I'm going to end up with is the limit. I'm going to have some constant on top, which is 12 times 11 times 10, all the way up to 1. And on the bottom, I'll be left with, okay, well, in the next step, this 2 disappears, so e to the x is the one that's going to survive. So if I take a constant and I divide by infinity, that means this limit is equal to 0. Let's take a look at the next one. All right, so now, this time we're no longer letting x go to infinity, we're letting it go to 0. and I'm looking at the function tangent of x minus x divided by x cubed. Well, the graph of tangent looks something like this, right? And then it just repeats like that periodically, where this is pi over 2 and minus pi over 2 or something like that. And that means that as x goes to 0, tangent of x is 0, and I have 0 minus 0 on top, so the top goes to 0 and so does the bottom. So let's go ahead then and apply L'Hopital's rule, this time by the 0 over 0 case, and take derivative. So derivative of tangent is secant squared. Derivative of x is 1 divided by 3x squared. And as x goes to 0, secant is 1 over cosine, that's going to be 1 over 1, right? And 1 minus 1 is 0. On the bottom, I have 0 again. So again, I have the 0 over 0 case for L'Hopital. So this is the same as the limit as x approaches 0. And now, on top, I need to take derivative one more time. And the way I want to look at this function is, I want to look at it as secant of x quantity squared, so that I can apply chain rule. So the 2 comes down, secant to the first, times derivative of secant, which is secant x tangent x, just like so. Derivative of that 0 of 1 is 0, so we don't write it anymore, divided by 3 times 2x to the first. Now, as x approaches 0, the question is, what does this approach? What I'm going to do next, instead of thinking about what secant does and what tangent does, I'm going to split the tangent as sine over cosine. And so I'm going to rewrite this as the limit as x approaches 0. And what do I have on top? I have 2 secants here, which is 1 over cosine. But I have another 1 over cosine from the tangent. So it's going to be, instead of secant squared, it's going to be secant cubed times the numerator of tangent, right? Because this tangent is sine x over cosine x, which is the same as sine x times an extra secant, which I grouped over here. And this is now divided by 3 times 2x. And we recognize this limit from before. We know that as x approaches 0, sine of x divided by x approaches 1. Secant is just 1 over cosine, so that's 1 over 1. The 2's will cancel, so I'm just left with the surviving 3 in the denominator, so this limit is 1 over 3, just like that. So this was a little bit longer, right? And we had to apply L'Hopital's 2 times. But you have to be familiar with these trig functions, right, and how they work, so that way you make your life a little bit easier. Because if you had tried to do another L'Hopital's here, notice that you have a product of 2 functions, right, secants and tangent, and then you have to use product rule, which makes the numerator become very complicated. But by switching tangent, writing it as sine over cosine, which is the same as sine times secant, I take the secant, I group it with the other 2. I know that secant goes to 1, so that doesn't bother me anymore. Sine x over x, so that doesn't bother me anymore, and I'm done. Right? I made my life a little bit simpler. Let's do the next one. So this time I have the limit as x approaches 0 of 1 over x to the power x squared. So let me go ahead and rewrite this a little bit. This is the same as the limit as x approaches 0 of x to the power negative x squared, right? So instead of writing it as a fraction, I'm writing it like this. And we saw in class that the technique to solving this type of problem is to apply natural log of both sides of this equation that I wrote here. So the natural log of my limit is going to be the natural log of this expression here And because the natural log is a continuous function, what I'm able to do is pass the log inside the limit. So this is the same as the limit of the natural log of x to the power minus x squared. And now I use the properties of the log to bring this exponent in front. So this is the same as the limit of negative x squared natural log of x. And I'm still not done because I still haven't obtained a fraction here, right? Remember, L'Hopital's requires us to have a fraction, but I can easily fix that by simply saying bring the x squared in the denominator and write it as 1 over x squared. So this is the same as the limit, and here's my fraction, ln of x divided by negative 1 over x squared, just like that. And now, as x approaches 0, ln goes to minus infinity, and so does this function, the negative 1 over x squared. So now I apply L'Hopital's finally, right? So this is the limit. Let me write it over here because I'm running out of space. So it's the limit as x approaches 0. Derivative on top is 1 over x. Derivative at the bottom is negative 2 comes down with the minus sign, so it's just positive 2. And I have 1 over x cubed, which I'm going to bring on top as just an x cubed. And of course, one of the x's will cancel, so the limit as x approaches 0 is just, I'm looking at x squared over 2, which is 0. So what I found is that the natural log of the limit that I'm trying to find is 0, which means what? It means that L has to be 1. And we saw in tutorial in class, we saw that sometimes we have to look at a difference that is going to give us infinity minus infinity. And the way we fix that problem is we call this number L, and I want to turn this into some kind of fraction. So instead of taking natural logs, I'm going to raise e to both sides. So I have e to the limit L is equal to e to this minus that, right? And I'm able to pass the exponential function inside simply because it's a continuous function. And now e to this, well, I have a difference of exponents, so that automatically gives me the following fraction. I have e to the cubic root of x divided by e to the natural log of x. And notice that as x approaches infinity, the top goes to infinity, the bottom also goes to infinity because I have ln going to infinity and e to infinity goes to infinity. So I now apply L'Hopital's in the infinity over infinity case. So this is the same as the limit of derivative on top is going to be e to the cubic root of x, which is the same as x to the 1/3, but now I have to multiply by the derivative of my exponent. So the derivative of the cubic root is 1/3 x to the minus 2/3, and on the bottom, well, e to the ln x is just x, so that derivative is 1, and as x goes to infinity, what do we get? We have e to the cubic root of x I have a 1/3, so I'm just write a 3 in the denominator, and I'm going to have x to the 2 over 3 like this. I'm bringing it in the denominator because the exponent is negative. Now x to the 2/3, that goes to infinity. E to the cubic root of x goes to infinity, so I have to apply L'Hopital's one more time. It's by the infinity over infinity case. This is the limit of let's see, what do we have? Again, I have to take another derivative on top. It's the same one as before. It's e to the cubic root of x times 1/3. So I'm just going to put a 9 in the bottom, right, with this extra 3. X to the minus 2/3. And then we have on the bottom, the derivative is going to be 2/3 x to the power minus 1/3. Okay, so far so good. Let's see what we end up with now. Let me simplify this a little bit. So I have the limit. I have e to the cubic root of x on top. Bring this in the denominator. So it becomes positive 2/3 minus 1/3. It becomes x to the power just 1/3, which is the cubic root. And then I have 9 divided by 3 is 3. 3 times 2 is 6. Okay, so far so good. But now, again, it happens that the top and the bottom go to infinity as x approaches infinity. So I have to apply it one more time. And hopefully this time it'll work. I have the limit e to the cubic root of x times 1/3 x to the minus 2/3. And on the bottom I have 6. And now notice I have the same exact derivative, 1/3 x to the minus 2/3, which finally gets rid of the x. So I have 1/6 times the exponential, and the exponential goes to infinity, so this limit is infinity. So what did we find? We found that e to our limit is infinity, which means that the limit itself had to have been infinity to begin with, right? Because the only thing that I can do is to get infinity here is if the exponent of e goes to infinity. So that was a little more complicated than the one we did in tutorial, right? There were many steps involved, but it still works. Let's do one more. So this is, let me write it a little bit bigger so that it's easier to see, is the limit as x goes to infinity of x to the 3 to the minus x, right? So I have some exponential here. I'm going to let this be L, because just like in the previous problem, I have to somehow undo this. And I'm going to take natural logs. So the ln of my limit is going to be the limit of 3 to the minus x ln x. And this is as x goes to infinity. So I might as well bring this 3 to the minus x in the denominator and write it as 3 to the x, just like that. Okay, now I have a fraction. The top goes to infinity, so does the bottom. So now I use L'Hopital's infinity over infinity case, which means this limit becomes the limit, and on top I'm going to have 1 over x. On the bottom I'm going to have derivative of 3 to the x, which is 3 to the x times natural log 3. And let's think about what happens now. The 1 over x function does this as x approaches infinity, so it goes to 0. So I'm dividing a very small number by something very large, which means what? I should get this is 0. So if the natural log of my limit is 0, that means that L had to have been 1. Okay? And for the final problem for this section, I put something that lets us show that for interest that's compounded continuously, the accumulated value is the principal amount e to the rt, where r is the interest rate as a number between 0 and 1, and t is some time interval that is bigger than 0. So the limit is this one here, right? And we know that as I compound more and more times, n is the number of times I'm compounding per time period, if I want to compound continuously, I have to let n go to infinity. So let's try to compute this limit. I'm going to call it L, and I'm going to take natural log of my limit L. Well, this is the same as the limit as n goes to infinity of n times t, so I'm bringing the exponent down, natural log 1 plus r over n. T is just a constant, I can bring it in front, so it's t times the limit. I'm going to write the natural log like this and divide by 1 over n. So now I'm turning this into a fraction. As n goes to infinity, this is just ln of 1, which is 0, and this is 1 over infinity, which is 0. So now this is the 0 over 0 case that allows us to use L'Hopital's rule. So let's go ahead and do that. So I need to take derivative on top, and I'm doing the derivative with respect to n, the variable n here. So I'm treating n now as a continuous variable, and I'm taking derivative with respect to that. Let's see what happens. I have t times the limit as n goes to infinity, derivative with respect to n on top. Well, okay, the inside of that function is the same as n plus r over n. I get 1 over that, so I'm just going to write it as a reciprocal n divided by n plus r times the derivative of the inside. So I'm going to use this form to take derivative of the inside. This is r n to the minus 1, so it's times negative r n to the minus 2 divided by, and this is just derivative of 1 over n, so it's negative n to the minus 2. So that lets me cancel the n to the minus 2 and the negative sign also. And now as n goes to infinity, this is just the limit of a rational function, right? Where the leading exponent is n to the first, the leading coefficient is 1, so the limit here is 1 divided by 1. So this whole thing should be t times 1 over 1, and I'm left with the extra r there, so this is rt. So what do we find? We found that the natural log of our limit is rt, and if I want to find L, I raise e to both sides, so the limit L is e to the rt, and that is exactly what shows up in the continuous compound interest formula, right? Is that function e to the rt. So that's where that arises from. That is why this is the formula for compound interest. It comes from this limit. Alright, so that's it for L'Hopital's rule, and I will put some more videos online for sections that I think are appropriate.